So this is what we looked at last time. Now, let's review this just a little bit. It would take the same amount of time to get to our dashed line, right? It would take the same amount of time. So in that time period, this is one wave. This is one wave. But here I can get two waves in. So this is double the amount of waves as A, twice the amount of waves, twice the frequency. But when you have twice the frequency, what about the wavelength? It is half, right? Now we go down here, we have twice the wavelength as A, but how many waves do we get? We only get half a wave. And down here, we have how many waves in that time period? 1, 2, 3, we get 4. We get 4 waves in this time period. 4 times the frequency, but what happens to the wavelength? It's a lot shorter. When you get all done, what's the speed of all these waves? Exactly the same. You cannot change the speed of that wave unless you change the median it is going through typically. We call it a median or something like that. So if you hit railroad tracks, that sound wave is going to go through that railroad track really fast compared to in open air. So we know that the speed of this wave is v is equal to lambda f. Let's say the speed is 24. You can't change it. If the speed's 24, the wavelength is 2. What's the frequency? 12, right? Well, I'm going to decrease my frequency to 4. If I decreased my frequency to 4, the wavelength has to change, right? You mess with either wavelength. If you mess with wavelength, frequency changes. If you change with frequency, the wavelength has to change. So if my frequency goes down to 4, my wavelength goes up to 6, right? You have to maintain the same speed of the wave. So your frequency here can go up to 24. If it goes way up to 24, what's your wavelength? Your wavelength goes way down to 1, right? So again, you do this with sound when you can change the treble and bass of sound. You're changing the frequency, which in turn changes the wavelength. But you're used to saying, oh, it's a frequency difference. And there's a wavelength difference as well. So again, if you adjust one, the other has to adjust to maintain the same speed. So we looked at that. Now we are going to look at simple harmonic motion. So, and I got some videos of this. So simple harmonic motion is periodic motion in the absence of friction and produces a restoring force that is directly proportional to the displacement and oppositely directed. An example of that is just a spring. So if I take this spring on the back of this, or any spring for that matter, if I pull it down, there's a restoring force opposite of my force down that is going to make it come back up. And we could send this into oscillating motion as well. So I'm going to show you some examples of that with some videos. These videos are old. These are, at one time, the National Science Foundation put together the best videos ever done and put them on into one collection, and this is some of those. There's a restoring force here the whole time, right? the glass as he moves it, what's it going to look like?
The trace that the pen makes will be a displacement time graph of simple harmonic motion. Very nice. You sure this is simple harmonic motion? Oh, I guarantee it.
Yeah, they're not actors. So we could figure out the slopes of all these to get displacement graphs. But here's another simple harmonic motion coming up.
You can think of circular motion as having a horizontal component and a vertical component.
Now, there's an example of if you have a light up here, as this thing goes around, all you do is have a light up here. What would the shadow of this knob look like down here? It would simply look like it's going back and forth, correct? That's all you would see.
When I turn this sideways, you see the vertical component of the motion. The spot appears to move up and down in a line, and it looks like simple harmonic motion.
Now, this is a dry ice puck before hockey tables, air hockey tables. This is dry ice in here. Dry ice goes directly from a solid to a gas, correct? So it floats on its own gas of carbon dioxide, frictionless. What do they got moving this?
There's a connection between uniform circular motion and
So the dry ice puck is suspended, is hooked to springs, right? And they created the same period, the same time, and the same frequency.
simple harmonic motion. This is periodic motion. Is it simple harmonic motion? This is a spring balance, and it's calibrated in newtons. I'm going to hook it onto the puck and pull the puck away from its equilibrium position and measure the force. It's now at the 10 centimeter mark, and the force is 1.1 newtons. 20 centimeters, 2.2 newtons. 30 centimeters, 3.4 newtons.
This is our first example.
40 centimeters, 4.6 newtons.
Okay. Simple harmonic motion. Simple harmonic motion. There's a period that you could...
Periodic motion that varies from here.
Okay. So this is Hooke's law for a spring. This K is a spring constant. It is negative. I will not put that negative in there, but realize it's this fact, because if I am pulling down, and if I say down is positive, the spring is acting, pulling with a force that is opposite my direction, correct? So no matter what, the restoring force is opposite. You know what? I'm just going to, when you get this K value, just make it, it's going to be a positive number. We're going to treat it as positive.
So I don't need to write down all these negatives?
No. Just realize that it's a force opposite. So typically, I don't put that negative in there. Just assume that you know it's acting opposite. So this is a spring constant then. Typically, if this is a spring constant, this is going to be in newtons per meter. And this is going to be the distance that spring is pulled out in meters. Now, you did something like this when you loaded your projectile launcher. Right? You loaded your projectile launcher and you measured the force and you measured the distance. If we simply take a spring if we take a spring like this and hang some weights on it, and measure this distance, that would be a small amount of weight, right? More weight. I can measure this distance x, and I know how much weight I have on here. It is very simple to get a spring constant. The more stretch you have, the more force, right? This is not a constant force. So when you graph this, it would look like this, where this is our displacement x and this is our force in newtons. What is our force in newtons? It's mg. Now, if we know that slope is equal to change in y over change in x, right? Oops, sorry. If slope equals change in y over change in x, what's changing on my y values is what units? Newtons, right? On my y, on my change in y-axis is newtons. And on my change in x-axis is in meters. And again, the more stretch of the spring, the more weight, the more force, right? This is a linear relationship, but it is not a constant force. It is a constant force would be a horizontal line, right? So it's very simple to get a spring constant. You can simply just keep adding weights and measuring that. Yeah, and I don't know if they were measuring. They still had the other one hooked on, so the one that was stretching this way might have been fighting the other one that way. I'm not sure how they did that one. I haven't calculated that one yet. They're stretching one and pulling the other one. So this is example 16.1. If we're looking for a force constant, we're looking for K. I'll put this in, but so what is a force constant when this is a car settles 1.2 centimeters when an 80 kilogram person gets in? Well, this 80 kilogram person is going to supply a force of weight mg. I want this distance to be in meters. How many meters is this? 0.012 meters. So 0.012 meters, my mass of 80 kilograms, 9.8 meters per second squared. This would produce a spring constant of 0.012. What do we get for a spring constant? $65,300 Newton meters, yes. This actually would work out. If you tried to make this sign convention work, you'd say it's in the negative x direction and g is negative, but we'll report a positive value. So, Hooke's law, this is example 16.2. This might be our next lab, not sure yet. So, we can use toy gun spring mechanism to ask and answer two simple questions. How much energy is stored in the spring of a tranquilizer gun that has a force constant of 50 Newton meters and is compressed 0.15 meters? Well, let's go up here and do A first. So we know what K is. Newton meters. We know X is 0.15 meters. How much energy is stored in that, and the elastic potential energy is given by 1/2 kx squared. Now, this looks like what? This looks like the formula for kinetic energy, correct? 1/2 mv squared. So this is elastic potential energy.
Why doesn't the it has all the same what's the last?
As far as getting energy of that, but we're not getting just force, we need energy, so we need we got to get this in joules. So joule is a Newton times a meter. So we would not get the same units. So our elastic potential energy, 1/2 50 Newton meters times my x squared, which is 0.15 meters squared. So this is going to produce a unit of what? Yeah, this is going to end up being joules up. Yeah, this is joules, and the joules is the same as what? Newton. This is going to end up being a Newton times a meter, right? So we get, what do we get out of that? 0.5625 joules. So elastic potential energy. EL, Almost looks like I got double L's. Now, if you neglect friction and mass of the spring, what is the speed will a 2-gram projectile be ejected from the gun? These things are just garbage. They're just garbage. These things, no. When Bob was a kid, these things would shoot, you'd put a number 2 pencil, basically. You'd have a number 2 pencil with a suction cup on it. That's how dart guns used to be. They were wood. That's essentially what they used to be. So now we know that if we compress this spring, okay, now the spring is locked back here. I should leave it like this. That distance in our problem is 0.15 meters or so, and obviously if we shoot this out, we should turn that elastic potential energy into moving kinetic energy, right? So that's what we do. We set these equal to each other, and we know that the elastic, I'm going to write this E out correctly, my elastic potential energy should be equal to my kinetic. So let's do this without the previous answer. So we would have 1/2 kx squared equals 1/2 mv squared. Does that help us at all? It doesn't. We can't cancel anything out, so I guess we could cancel out the 1/2. We could solve it with this. So if we solve this for the velocity, we're going to end up with kx squared unit-wise it will. Kx squared divided by meters, and then we're going to have to do what? Square root that. So let's make sure we got our units correct. We've got room to do it here. We've got 50 Newton meters, 0.15 meters squared. What mass are we going to put in here? .002 kilograms, right? And then what do we get out of this? 61.8. What do we get? $23.7. I think that should be right. The easiest way to do some calculations on a dart gun is to shoot it straight up in a stairwell. So if you're at the bottom of the stairwell and you've got an open stairwell that hooks around, then you can kind of figure out how many blocks up it went. And that would be potential energy, gravitational potential energy, based upon the height, should equal the kinetic it comes out, should it came from the spring. Okay, so we looked at this yesterday. Period is the time just for one complete oscillation. T will be in seconds. So unit-wise, you think of it this way, seconds per revolution. Seconds per revolution. You're not going to try to time one revolution. You've got a spring going up and down, or we'll do a pendulum. We'll do that lab for sure. If I'm doing this back and forth, I'm not going to try to time it, start and time it on and off for one. I'm going to let that go back and forth 10 times. I'll let the clock go for 10 revolutions back and forth. So this period is in seconds per revolution. Typically, you're just going to see seconds. And then we also said this frequency is 1 over the period. So if that's 1 over the period, your units are going to be revolutions per second. The revolutions or oscillations, whatever you want to call it, is not going to be there. This would be seconds to the minus 1 because it's in the denominator. Okay. Before I do this problem, let's do something you can maybe relate this to for frequency and wavelength. FM radio. What station do you listen to? .5. We'll use that. 104.5 is what number? What is it? 104.5 what? Megahertz. Okay. FM is megahertz. Somebody give me one station on AM. Anybody? 580. And that is in kilohertz. Okay. So AM will start at maybe 500, go up to almost 1500, but that is in kilohertz. What is the speed of an electromagnetic wave? It is 3 times 10 to the 8th meters per second. This is the speed of light, the speed of electromagnetic wave, the speed of our radio station signal. 3 times 10 to the 8th meters per second. Yes, those electromagnetic waves, yes. Through air, yes. So, my question is, what is the wavelength of these waves? So, we know that V is equal to lambda F, right? This is the velocity of our wave. Then we know that V divided by F will give us our wavelength. Now, What travels farther, AM waves or FM? Can you listen to AM station farther away or FM? AM by far. You can listen to Chicago on AM. So you could pull stations out of Chicago, maybe Kansas City on AM. AM by far. Now, if we calculate this then on this first one, 3 times 10 to the 8th meters per second divided by 104.5 times 10 to the what if it's mega? 10 to the 6th. That's our wavelength there. And for this one, 3 times 10 to the 8th meters 80 kilo is times 10 to the 3rd hertz. Grab your calculator. You can put them in just that way. What do we get? Three to the 8th divided by 104.5 to the 6th is 2.87 meters. .4 feet is the wavelength of the country station wax 104.5. Right? 2.87 meters. On AM, this is 517 meters, which is 1,697 feet. That is one big difference, right? The frequencies are different by a factor of 1,000 or so. These wavelengths are drastically different. An AM wave, drastically different. What's that? Because AM gets blocked out by there's a lot more static and interference. Electric fencers for cows you could buzz in on your AM station. The Durand Bridge, when I was a kid, we'd go across the Durand Bridge, which had a metal top, and the station would cut in and out as you went across the bridge on AM. So AM has a lot more interference and things like that. You get a better, clean signal. The same thing's going to happen with 5G coming up. And I wish I knew a little bit more, but 5G, well, that's coming. These antennas are going to be like 50 meters apart. There's going to have to be antennas everywhere compared to what it is now. What's that? Well, the antennas. So it's interesting because Huawei, the Chinese company Huawei, which has stolen all the American stuff and other stuff, is the leader in 5G, and they're worried about them selling equipment in America and Britain and implanting secret stuff. I don't know if the gal's in Canada yet or not. I don't know if we released her or not. Yeah. But they're the leader kind of in 5G. Okay, so frequency of 2 oscillations in medical ultrasound.
I'm out.
No, you're not. So we can use the formula presented in this module to determine both the frequency based on known oscillations and the oscillation based on a known frequency. Let's try an example of each. A medical imaging device produces ultrasound oscillating at a period of 400. What is this? Fancy us? That is micro. So this period here is 0.4 micro is a millionth, so this is times 10 to the minus 6 seconds. That's the period.
Zoom out.
Yep. So if that's the period, my frequency is simply 1 over the period. This is micro. And a micro is 1/1,000,000th. So that's how I get 1 times 10 to the minus 6. So 0.4 to the minus 6 this gives us a frequency of this frequency comes out to be 2500,000 hertz. Sorry. How many million is that? Yeah, so you could put this in then. The ultrasound frequency is going to be 2.5 megahertz, right? Well, this is 2,500,000, right? This mega is a million. So that would be 2.5 megahertz, right? That's the period of one wave. 0.4 times 10 to the minus 6 is the period for one wave. That versus a 264C. I don't know if I got a 264C. I got a 2 pretty close to this. Anybody hear that? You can hear that? That's pretty good. So, in this one, my frequency is 264 hertz. It wants to know what the period is. These are reciprocals of each other. So we'd have 1 divided by... Now, what unit should we get out of this for a period? What unit should we get? Seconds, right? This is in hertz. What is hertz? You could put this number over seconds, right? So that when you divided this, we're going to end up with a number in seconds. This would be fine, right? This is 1 over x, which is equal to x. We got to get seconds for a unit out of this. So if we did this, we would get 0.00379 seconds. Now, if you put these into simple harmonic motion with a spring going up and down, we can derive these equations for frequency and period. So 1 over 2 pi times the square root of our spring constant divided by our mass, or our period. If we solved it for our period, it would look like this. And again, this would simply be a ball on a string that I showed you, that one. No. 2 pi is just 2 pi for numbers. Let's do this one down here, and then this is going to take us right out. So, shock absorbers on a car go bad, and then the car will oscillate, especially if you got a bunch of people in there, such as going over bumps, and then after you go over the bump, it's going to keep oscillating. Calculate the frequency and period of these oscillations for such a car if a mass is 900 kilograms and the force constant K is 6.53 times 10 to the 4th. So we're looking for the period of frequency. Calculate the frequency and period. All right, let's just do frequency, because then we can just go 1 over f. This is just going to be simply 2 pi times the square root of k, 6.53 times 10 to the 4th, over my mass. Yeah, 1.36. So my period would be 0.738 seconds. All right, I will send you out an update of which homework ones to look at after class here. And the take-home quiz I don't have done yet, but I'll try to work on that as well. Okay, so in the homework problem, I'll send you out an email.